binomial table is table 6 in our textbook. That's found on page 822, and these tables are also posted in Canvas. So the way you read these tables is you have the number of trials. So here we were doing an example with 5 trials, and then there's all sorts of different probabilities, and that represents the probabilities for a success. So in our case, the probability of success was 0.4, and we would get the probability distribution. X equals 0 is 0.078, x equals 1 is 0.259, x equals 2 is 0.346, which we did by hand. Then the remaining 3 are 0.230, 0.077, and 0.011. So the table itself is not that hard to read, but the problem is we have the case of n equals 5, the case n equals 10, and n equals 15, n equals 20, 25, and I think that's it. Yeah, that's all that we have. So what if you have a different number of trials? So that's where there are some limitations for using the binomial tables. It's fine if you have a very extensive table or you're using a multiple of 5 for your number of trials, but if that's not the case, or if your probability of success is not here on this in the table, then you need to have some other tool available for you. So one such tool is to use the formula for the binomial distribution. So to have x successes among n trials, you have that combination formula where you have n factorial divided by x factorial times n minus x factorial, then the probability of success raised to x, that's the number of successes, and then 1 minus the probability of success raised to the n minus x. So that x and n minus x, x will be the number of successes and n minus x ends up being the number of failures. So that's the formula we can use. We're going to use it exactly one time and then we'll use technology from here on out. So example 6.27, this was a strange study, but these kinds of studies actually happen. Researchers were interested in whether college females could detect their roommate from smell alone. So they created this experimental situation where the people in the study were all given fragrance-free everything. So fragrance-free soap, shampoo, laundry detergent, everything. And they had the people in the experiment wear just a plain white shirt and sleep in it for, I don't know, maybe 6 or 8 hours. And then they gathered the shirts, put them into little bags, and presented a roommate with these 3 shirts. One of them was worn by her roommate, and the other 2 were just worn by other people in the study. And the question was, can this woman detect her roommate just by scent? And so in this case, this experiment, they had the trial done twice. So she picked the shirt that she liked, or the one that smelled like her roommate, and then they folded the shirts back up, they put them back into the baggies, they moved it around, and had her pick again. So it was the same 3 shirts, but they wanted just to have her do this trial again. So we're looking at 2 trials here, and we'll assume that they're independent. Maybe that's a little bit of a stretch to do that, but we'll assume they're independent. And the probability of success, we're going to assume for just a minute that she cannot identify her roommate by smell. She's just randomly guessing. So if that's the case, the probability of her randomly guessing would be 1 out of 3, because there are 3 options and she would pick the correct one 1 out of 3 times. So in this study, if she's going to be presented with these shirts twice, she either can correctly identify the shirt no times, one of the 2 trials, or both trials. So let's calculate the probabilities. What's the probability that she does not identify this shirt at all? So we start with the 2 trials, and we want to have 0 factorial and 2 minus 0 factorial, and then 1/3 to the 0, and then the probability of failure is 2/3, and we want to have that twice. Now, a note here, 2 minus 0 will be 2, so that's 2 factorial over 2 factorial. That's going to go away, and 0 factorial equals 1. There's only one way to rearrange no numbers. It's kind of a weird thing, but 0 factorial is 1. This is the last time you're going to have to use this formula, though, so keep that in mind. So don't stress out too much about this formula. 1/3 to the 0 is just 1, and so we just need to do 2/3 squared, and as a decimal, that is 0.444. I'll go ahead and do a 4th 4. Usually probabilities, I'll do 4 decimal places. Now for 1. So here we have 2 trials. We want 1 success, and then 2 minus 1 failures. Then we'll have 1 success, and then we'll have 1 failure. So in this case, 2 factorial is 2, and then 1 factorial times 1 factorial is just 1. That's times 1/3 times 2/3, and this actually also gives you 0.4444. And then the probability, if she was just guessing that she would get them both correct, would be 2 factorial over 2 factorial, and then 1/3 for both of them, and 2/3 none of the times. And so those all cancel, and so we're looking at 1/3 squared, and that gives you 0.1111. So randomly guessing, the probability that she would never identify the right shirt or identify it 1 out of the 2 times is 0.4444, and then 0.1111 is a probability that just guessing that she would correctly identify. So this is kind of a preview of what we're going to be doing next section when we're looking at these proportions, when we're looking at how they behave. If she was randomly guessing, she would only identify the shirts both times 11% of the time. And in this particular study, they actually found these results. 47.7% of the subjects identified correctly on 0 trials. Okay, that's actually pretty close to what the guessing probability would be. But look at these next two. 22.7% of the time it identified correctly on 1 trial compared to our 0.44. That's a bit different. And then this one, this 31.7, is incredibly different from the 11% that we had. So we expected with random guessing that 11% of the time this would happen, and really it was 31.7% of the time. So what this means in context of the study is that some women really can determine which shirt was worn by their roommate. So they can identify their roommate just by scent. Because 11% is what would have happened if she was just guessing. 31.7% is a lot different. So some of these women are actually doing a pretty good job.